The trail of discovery and development leading to the design and construction of B-Reactor at Hanford begins in the last decade of 1800. We begin with the atom, a word that comes from the Greek word atomus, meaning indivisible. Until that time, it was believed that all matter, everything in our universe, was composed of these indivisible particles. It was understood that the atoms of different materials were unique, and up to that time, about 70 different atoms or elements had been discovered. But there was beginning to be a belief that maybe the atom did have more than one part. And finally, in fact, in 1897, Joseph John Thomson, an English physicist, discovered what was eventually called an electron. He identified it as part of an atom. He proved that it was much smaller than the smallest atom, hydrogen, by a factor of almost 2,000, and that it had a negative electrical charge. He believed it orbited around the rest of the atom, now called the nucleus, like the Earth around the sun. So as we entered the 20th century with respect to experimental physics, that was the state of our knowledge of atoms. Science moves ahead both in theory and in experiments, and in 1905, a theoretical physicist was having what would later be called his miracle year. A young German, Albert Einstein, had a new PhD, was brilliant in math and physics, but so-so in other subjects. So he'd failed to get the teaching job he'd hoped for, and had to settle for a position as a patent clerk in Bern, Switzerland. His work there did give him time to think about the world around him, and he developed and published 5 of his famous theories that year, one of which would have great significance to our story. This was his proof to the satisfaction of his peers that energy and mass were related, and that every bit of matter, every atom, contained energy, and the relationship between the two was his famous formula E equals mc squared, where E, energy, is equal to m, mass, multiplied by the speed of light, c, an enormous number, squared, which is a super enormous number. What it meant was that a kilogram, 2.2 pounds, of matter, any matter, contains an enormous amount of energy locked up in its atoms. How much? Well, 25 billion kilowatt hours of energy. That's equal to the electrical energy output of a large power reactor operating for 3 years. That's a year's supply of electrical energy for 1.6 million households. How do you release that energy? Well, at that time, no one, including Dr. Einstein, had any idea. His formula just said if mass disappeared, it would be replaced by energy. Moving back into the laboratory, now that scientists understood the existence of electrons, they found ways to strip them away from atoms, leaving a positive charged nucleus, which they called an ion. The helium ion was determined to be identical to a part of radiation given off by radium, and was given the name the alpha particle by Ernest Rutherford, working at Cambridge in 1917. He used alpha particles to bombard nitrogen atoms, which resulted in 2 very important discoveries. First, he was able to cause the nitrogen to change or transform into oxygen. Second, when this happened, another particle was released, which had about the mass of a hydrogen atom and was positively charged. He named this particle the proton. Now the atom was understood to have at least 3 parts, electrons and protons, in addition to the remaining nucleus. The search for the mystery of what might be left in the nucleus began, and in 1932, James Chadwick, also working at Cambridge, discovered another particle, which had the same mass as a proton, but was without any electrical charge. It was a neutral particle, and he gave it the name a neutron. Now the atom could be characterized as having neutrons and protons in its nucleus, and electrons spinning around the nucleus. The discovery of the neutron was a yet unrealized world-changing event. At this point in our history, we meet a vital key player, Dr. Enrico Fermi, an Italian physics professor. He had an interest, like many other physicists at the time, in trying to transform atoms by bombarding them with subatomic particles. But he recognized that the neutron could be a superior particle to use, Since having no electrical charge, it could not be repelled by the positive charge of the nucleus of the target atoms. He and his team, using a neutron-generating chemical reaction of their invention, began bombarding atoms of different elements. And in many cases, they were successful in creating new isotopes. In each case, the new atom was an isotope of the next heavier element in line in the periodic chart with respect to the target atom. Along the way, by accident, as often happens in experimental science, they discovered that they got better results when their experiment was done on a wood laboratory tabletop as compared to a marble tabletop. They concluded that the neutrons were bouncing off the light hydrogen atoms in the wood and were being slowed down before they reached the target, which seemed to make them more easily absorbed by the target. They said the neutrons had been moderated, and they decided to intentionally do this by placing a block of paraffin, which is carbon and hydrogen, between the neutron generator and the target atoms, and were rewarded with even greater success. They proceeded through the periodic table of atoms until they reached the heaviest, uranium. Here they got a reaction, but they were unable to identify the end product. At this point, they published their results, and this led to a Nobel Prize for Fermi. The 1938 prize was for the discovery of new isotopes by irradiation with slow neutrons. Fermi's wife was Jewish, and seeing the terrible things beginning to happen to Jews in Germany and Italy, he convinced the Italian government it would be a great honor if his whole family would accompany them to receive this Nobel Prize. They packed as if for a short trip, but after receiving the prize, they sailed for the United States, joining a large number of other scientists from Europe who were fleeing for the same reason, including Albert Einstein, who was already gone to the US. The path of our history now moves to Germany, where a PhD chemist, Otto Hahn, and a PhD physicist, Lisa Meitner, with a 30-year working relationship, have now begun to investigate the Fermi experiments with slow neutrons and uranium. Before they can conclude this work, Lisa, as a Jew, finds it necessary in the summer of 1938 to flee to Sweden. They continue to correspond, and in a letter in late December of that year, Hahn tells Lisa that when he and his new partner bombard uranium, they encounter the same puzzle that confronted Fermi. What is the final product? Hahn is convinced that one thing left behind seems to be the element barium. It turns out that when she receives this letter, Lisa's nephew, Otto Frisch, who is a respected physicist working in Denmark, is visiting Lisa in Sweden. The two of them begin to ponder the puzzle in a very interesting setting for what will be a world-changing event. They carry on their discussion of this problem as they walk through a light snowfall, and finally sit on a fallen log and start to make some calculations on scratch paper from their pockets. Lisa insists that if Hahn sees barium, it must be true, because she knows him to be a careful and superior chemist. They then make the scientific jump that no one has ever made before, except for another lady we'll meet later, and they conclude that possibly the uranium atom has broken into parts. If it broke into two parts, just counting the protons, if one part was barium, then the likely other part would be krypton, which is a gas and could easily escape detection if one were not looking for it. Then Lisa calculates that if these were the two elements left behind, the combined atomic weight of the two would be very slightly less than the parent uranium atom. They then realize if this slight amount of matter had disappeared, there should have been an energy release according to the Einstein mass and energy formula. Frisch returned to Copenhagen, where he worked under the world-famous physicist Niels Bohr. When told of the conclusion of Frisch and Meitner, Bohr is reported to have smacked himself on the forehead and shouted, "Of course, why haven't we seen this?" As it turns out, Bohr is leaving for the United States on January 7, 1939, for a series of physics conferences. He advises Frisch to make his own independent experiments, to confirm the reactions, and for Frisch and Meitner to publish a paper describing their analysis. Frisch hurries to do these things, and in the process he asks a biologist friend what they call the process of cell division. Told that it's called binary fission, he and Meitner decide to call the uranium split fission. When Bohr reaches New York, he is met by a number of immigrant scientists, including Dr. Fermi. Soon word of nuclear fission begins to spread through the American scientific community, and many of them rush to their labs to verify the process. It's also at this time they begin to realize the dark side of this discovery, the potential for the release of enormous amounts of energy and the possibility of what would later be called atomic bombs. There's also the concern that these experiments began in Germany. The immigrant scientists know that many brilliant and talented scientists are still in Germany and other European countries because they studied and worked with them or under them. Having seen firsthand what was happening in Europe, the immigrant scientists began a two-phase campaign. One, to find some way to shroud further experiments and developments from the outside world, and two, to find some way to warn the American government of the potential consequences of the discovery, and to urge an all-out program for America to be first in future developments. They needed to warn the president. Imagine the problem of a number of foreign scientists, many with heavy accents, trying to explain to anyone in the government, including the president, that the little-known element uranium has the potential to destroy a city. They decided they needed a well-known spokesman, someone trusted by the president who could carry the spokesman's message. Since Albert Einstein was by far the best-known scientist now in America, and several of them had worked and studied with him in Europe, they recruited him to be their spokesman. Two men, Leo Szilard and Eugene Wigner, men who will continue to play significant parts in our history, composed a letter which Einstein signed. They found in their community a trusted non-scientist who was a good friend of the president to carry the letter and to assure the president that this letter and these people should be taken very seriously. The letter, delivered in September of 1939, worked to the extent that President Roosevelt started the action to financially support a focused research program to begin in this country. Now we look at one of the great what-ifs in our world history. Back in 1934, when Fermi was puzzled about his results when he bombarded uranium with slow neutrons, a well-respected PhD German chemist, Ida Nodak, wrote and published a paper and sent a copy to Professor Fermi, suggesting that instead of looking for a larger element than uranium to be the product of his experiments, possibly he should consider that the atom had broken into smaller parts, and that he should look in that direction. For reasons never fully explained, he ignored her. And more importantly, her fellow German scientists ignored her. What if someone in Germany had seriously followed up on her suggestion in 1934? What if they had done the Hahn-Meitner experiments at that time and arrived at Meitner's explanation before she was chased out of Germany? What if the German government had begun to secretly explore nuclear fission in 1934? This is the same government that developed jet engines and long-range rockets by 1944. Imagine at least a 5-year head start on the rest of the world in the pursuit of nuclear weapons. It's a chilly thought. Back to the experimental history. A very important discovery in several labs in 1939 revealed that when the uranium atom fissions, it releases 2 to 3 new neutrons. If one neutron can cause the release of 2 to 3 neutrons, and if those 2 to 3 can each cause the release of another 2 to 3, then it was possible that what was called a chain reaction could occur. Since these reactions would occur in a tiny fraction of a second, and since each fission also released significant amounts of energy, this led further to the possibilities of nuclear weapon. Another significant discovery occurred in 1940. It was determined that the uranium atom that fissioned was not the base uranium-238 atom, but rather a uranium-235 isotope. Uranium-235 is only 0.7% of natural uranium. The government program, considering the use of uranium as a fission weapon, now had to refocus on the uranium-235 isotope and how to separate it from the base natural uranium. Since isotopes are identical chemically, they can only be separated by some physical process, such as centrifuges, or electromagnetically, or by diffusion. The government program began work on all of the above to determine which method would work best. Also, in 1940, working at Columbia University, Fermi and Szilard now began to pursue the chain reaction possibility with uranium and slow neutrons. They finally selected carbon atoms in the form of graphite as the moderating material. And with government assistance to purchase uranium and pure graphite, they began to stack graphite blocks with spaces for uranium and make measurements of the generation of neutrons. In early 1941, they and this work moved to the University of Chicago. In other government research being carried out at the University of California in Berkeley, a PhD chemist, Glenn Seaborg, discovered that when uranium-238 is bombarded by slow neutrons, although it doesn't fission, it does absorb slow neutrons and then begins a transformation. It first changes to an unstable isotope of uranium, and then it quickly transforms itself into a new element, neptunium, which also has a short life and changes to a new element, plutonium. He then found out that the new plutonium element was very stable, but under neutron bombardment, it would also fission and release energy and multiple neutrons, much like the uranium-235 atom. The significant thing about plutonium was that being a different element than uranium, it could be separated from uranium with a rather straightforward chemical process. Then the world changes for the United States with the attack on Pearl Harbor on December 7, 1941. And the pursuit of atomic weapons in the U.S. goes from laboratory experiments to a military operation. More money is immediately made available to the labs, and in Chicago this results in the procurement of tons of graphite and uranium in order to build what Fermi and Szilard call a pile, in order to see if they can achieve the first controlled chain reaction. In the summer of 1942, they begin with bars of graphite that are 4 inches by 4 inches by several feet long, which have holes bored in them to accept pieces of uranium. They start with small piles to make measurements and continue to make larger piles as the materials become available. In the meantime, in the fall of 1942, the government establishes what became known as the Manhattan Project to centralize all control over the development of atomic weapons and appoints newly promoted General Leslie Groves as commander. With the discovery of plutonium, there was now another pressing reason to achieve a controlled chain reaction. In order to produce plutonium in the quantities needed, a massive source of neutrons would be needed, and it was believed the controlled chain reaction could be that source. In a squash court under the stadium at the University of Chicago, Fermi and Szilard begin construction of what they believe will be a successful demonstration of the world's first controlled chain reaction. This was a rather massive experiment. The pile eventually reached over 20 feet in height, was 25 feet wide, and contained 400 tons of graphite and 56 tons of uranium. It also had control and safety rods, which were wood poles sheathed in cadmium, which absorbs neutrons. It had no shielding and no cooling, as it was not intended to go beyond the demonstration that a chain reaction could be achieved and could be controlled. On December 2nd, 1942, they did exactly that, and the road to Hanford took a giant step. Assuming that the chain reaction experiment would be successful, 3 major events were already occurring. The first was the selection by General Groves of the DuPont Corporation to be the organization that would be responsible for the final design, construction, and operation of the entire plutonium production portion of the Manhattan Project. Second, at Chicago, a team of scientists led by Eugene Wigner was developing the conceptual design for the first full-scale production reactor. Wigner had a PhD in chemical engineering, but he was working primarily as a physicist, so he is exceptionally well suited for this assignment. They realized that to produce the quantities of plutonium that would be needed, that the reactor would need to operate at very high energy levels. This meant they would have to have a very large cooling source to absorb the vast amounts of heat energy that would be released by the chain reaction. Their experiments had given them the confidence that water could be used as the primary coolant, so they needed a production site that had a very large source of cooling water, in addition to a ready supply of reliable electric energy nearby to power the giant pumps that they would need. And lastly, they needed a remote site with lots of open, unpopulated space, since this project would still be an experiment. So the third major event was find a site. General Groves had chosen Lieutenant Colonel Frank Matthias for this task, and he and two DuPont engineers began a trip in late December to look for sites that might fit the criteria that had been established. They looked at sites in California and other western states before they flew over the Hanford area on December 22, 1942. What they saw was the mighty Columbia River flowing around several hundred square miles of mostly unpopulated area. They also saw power lines crossing in the area coming from newly constructed Grand Coulee Dam upstream and from Bonneville Dam downstream. This site had it all: an enormous supply of cold, clean water, a very large source of reliable electric power, and miles of flat open area, with very few people who would have to be displaced. They all agreed that this was the place, and when they reported their find to General Groves, he immediately agreed, and Hanford was chosen for the site of plutonium production and the site for the first production reactor, which came to be named B. And that concludes our history lesson of a 45-year trip from the discovery of the electron in 1897 to the choice of Hanford in 1942. Now we will introduce you to the reactor and give you a basic idea how it works, how it was built, and introduce you to some of the models and exhibits you'll see when you make your visit to B-Reactor.